Hello, everyone. Thank you for joining us today in this new Rhino User Webinar. I am Guillermo Varela from Mail Europe, and I'm here today with Bastian Nispel from Design to Production. Today, he will show us how to design, how the plugin D2P components can help us to organize and improve the performance of our Grasshopper definitions. And remember that in the last 15 minutes of the webinar, we will have some time for Q&A, so you can ask questions in the chat, and we will check them at the end. Also, I would like to mention that the webinar is being recorded and will be available on our YouTube channel probably tomorrow, where you can find all the webinars that we have recorded. And thanks again, Bastian, for accepting the invitation to this webinar. And please start with the presentation if you're ready. Thank you.
You're welcome, and thanks a lot for the opportunity to present our stuff. Yeah, hello and welcome. My name is Bastian. I'm working at Design to Production, or shortly D2P. We developed parametrics over the last 17, 18 years and condensed it into a framework which we consider to be the D2P components I'm going to present to you. So maybe as a heads from spaghetti to lasagna, I might apply this, but it's not about that. It's about how you structure your data. So yeah, then let's start here. So Design to Production projects all over the world. I think in the meanwhile, we did over 100 of those. Beautiful stuff. And we are closing the gap between planning process and the manufacturing process, while like coordinating all this complex geometry stuff. So this is about the planning. We do design optimization, we do parametric planning and fabrication data, but we also do consulting. We have a strong background in timber, so we do like timber consulting for timber construction, digital prefabrication, but as well BIM and DFMA. The third part we have in our services is software. So we develop planning tools, CAD and CAM plugins, and web applications. So any kind of tech stack you can think about, usually in the domain of architecture. So now I just want to fly through some projects we did over the last years to get you some inspiration. Some of them you probably already have seen, some maybe not. So that was a very short introduction of D2P. Now I directly want to jump into our modeling philosophy, because this seminar is going to be about the Grasshopper plugin in the end. But to better understand what's going on in the background, we need to talk about some theoretical topics. So the first thing we consider to be really crucial for our modeling approach is the multiscalar modeling. What does it mean? Well, we have a scale, we have two axes. In the x-axis, we have different stages. So let's say it's a building process. We have a concept phase, coordination, detailing, production and planning, and so on. And on the y-axis, we have different topics. So a context, design, material, engineering, fabrication, whatever, you name it. The classic way is we start somewhere here in time and we just refine a model. Yeah, we just have data, we have dumped data, we just refine it all the way down. So the question is, now that we start doing things parametrically, and it works like the waterfall approach from one to another, but how do we backtrack? How do we actually, if something changes, get back to a state that is still valid? Okay, this one is still the x-axis. So first thing we do here in this, like except for the standard processes, we define a stack of models. We call it context, reference, coordination, and detail model. And there are some additional ones where every model is like valid from the beginning to the end and completely in production tolerance from the first information to the very end of the process and project. The next thing we do on the other axis is that we kind of condense the information. So we have a context model in the concept phase. And you could say, okay, as an architect, I'm just interested in like the design, the early design, not really how it's going to be assembled or fabricated. But what we do here is we bring in our knowledge from fabrication and assembly in the very first steps in a more abstract way in order to be able to consult on the right information and geometry, so that we already in the beginning have optimized shapes, for example. And we iterate as long as needed, so to get certain state of the model to be able to build on top of that. And then we go to the reference model. But let's talk also about the model stack itself, that it's getting a bit less abstract. So why do we do this? In the end, we want to have, this is an example of Swatch, we want to have production data with an accuracy of like less than a hundredth of a millimeter. And in order to do that, we need like super sharp models from the beginning. We cannot just get rid of that and create production data in the end. That means we want to freeze in the process information we need in the end for production. In that project, in Swatch, we freeze the axes and layers in October 2013. That was the last change. We used those information to build everything else on top of it, like, for example, the reference surface 1 year after. That was the last change here. And in February 2015, we created all the beam axes, which in the end have been used for creating all the prefabricated pieces, because that's what we are doing in the end. We want to prefabricate stuff. Therefore, we need to have a different approach for planning. So now in a bit more detailed way, we talk about the models themselves. So we have a context model. This is ultimately responsible for defining the relevant and immutable geometric references, like, for example, the building grid and levels, the project origin, the orientation, survey points, building envelope, sectors, and the context, whatever that means, terrain, streets, and vegetation. The next model in the stack is the reference model. It defines the basic geometric properties of the project and can serve also for extracting first bill of quantities, defining nomenclature, setting up the whole process so that it scales afterwards. So classical geometry references here are the surfaces and axes. We have main components, which are just represented by, for example, beam axes or sometimes even undetailed volumes, and some nodes. So anything that is necessary to already place a component where it should be in the end. Next stage, and this is an important one, is a coordination model. This defines all relevant components and all nodes in the model, and especially in terms of fabrication, we need here to also place like connections, cutouts, no-fly zones that we can really talk with MEP, with the engineers and architects about how things should develop from here. Planks as well. So that's in the coordination stage. Afterwards, and this is all different scope. So where it's not about pre-project or pretender, we go to the manufacturing side, and they want to have, of course, production data. And therefore, we create detailed models where all components that will be fabricated are included with detailed volumes and fasteners and whatever's necessary to define all these fancy cutouts and shapes. Last step, what we usually do is to create a production model out of that with production-specific information. We need to specifically talk about machines, tolerances, positioning, nesting, and so on, and can potentially also export the CAM data, production lists, QA documents, whatever. So that was just a brief overview about how we set up our models. Now we go a bit more into detail to come closer to the process itself. It's about nomenclature. I want to start with a reference to the Zen of Python from, you probably know that one. And I picked some of the comments here. So for me, readability counts is very important in parametrics because we always need to talk about something, and it's better to explicitly define the wording. Next thing, which is super crucial, special cases aren't special enough to break the rules, although practicality beats purity. And this is something you can actually do with the components, we'll see later, because you are not completely wired to one computation flow. You can actually do some manual refactoring and still make use of the logic behind and apply your algorithms to it. So in the last one I want to share is the namespace R1, honking, great idea. Let's do more of those. All right. It's just an Easter egg. You probably know if you have a Python shell, you just import this and it prints the set of Python. All right, so this is about naming. Why do we need to name things? I think I already started to talk about this. Yeah, let's talk about the beam at the back wall on the left side from, I don't know. We don't know which one is meant, aren't we? But it gets easier if we classify. So if we find, for example, certain pieces or components that have similar attributes, similar behavior, we can give them a family. We can consider them to be of one component type. In that case, we say, okay, those are slab beams. We have infill beams, edge beams, raft beams, and purlins. Furthermore, we then identified that we might have within these types even subtypes. So here's a ridge, here's an atrium, and here's the reason why we introduced the subtypes, because, for example, yeah, those are shared geometries for all of them, attributes. And here we see, okay, this Perlin beam behaves still similar, but has a different width, different reference surface, whatever. So that's the reason why we introduce subtypes here, to be able to handle them programmatically later on. What we do as well from here on in the coordination process is we create a component type catalog. So what you see here are the types we just talked about, and they show up in Rhino. So this is already tooling like this. Yeah, they get a specific position in the layer tree, but we will cover this later on. The same we do for joints. So here we actually have exactly the component types we just saw in both directions, in X and Y, and create a matrix and kind of theoretically collide them against each other so that we get kind of, yeah, the joints, the potential joints. And then we have, yeah, these pieces, we have engineered drawings, and we try to identify the situations. Yeah. Same from here, we then extract from the matrix all the joint types and have a catalog. These are then the joint types, and they represent similar in the Rhino document. So they also be considered to be component types, but the joints are special. We will talk this through in a while. All right. Now it's already the last chapter here in the presentation. It's about syntactics and semantics, which is quite a deep topic here. So let's talk about what is actually a type and an instance, or component type and a component instance. The component types we have in the example project we will showcase in a few minutes are transversal beams and longitudinal beams. They are differentiated by color, and we just decided that it's probably a good idea to have, like, in one direction one type and in the another one. Doesn't have to be, but let's like play it through like this. Types in general, if you come from object-oriented programming, can almost equal a class. So they are a blueprint for a collection for similar behaving pieces. And as a rule of thumb, you could, like, say you can't select types in Rhino. That's a very, very easy analogy, but they are more like abstract blueprints. Second one are the instances. So same types have all different instances. We have, for example, this one is 200, 201, 202, 203, whatever, of type transversal beam. And those are the instances of the longitudinal beam. Yeah, so, and here is the same in object-oriented programming. A component instance equals an object of a class. And as a rule of thumb, you can select them in Rhino. Right. Next, we can go in a more detailed way into component types. So, as already said, we have them in the model like this in the layer tree. And here's now a small helper of how this name is being composed. And this is important later. We have the type ID plus a layer description delimiter and the type description. And this together leads to this schema. In the plugin, you just put in here type ID and the type description, and the outcome will be that one in the end. All right. Now let's talk about the instance. Instances. So instances are not directly showing up in the layer tree, but they are named, like in the object properties. If you select an object, you see all the objects inside of that group have the same name. And they are composed like this. So you have the type ID, type delimiter, and the instance name. And we have a component for that where you put in the information and in the end can bake it so that it becomes that one. So, all right, this is about the anatomy of a component. This might be a bit more clearer in a second as well when we start Rhino actually. So the basic setup for a component in Rhino is actually we need an instance name which replaces which in the end is represented by a text label and a plane. So this is the information. And this whole thing is inside of a group. So that's basically a very bare bone component for us. And then we can add a lot of information to that component. So this is a data container group with the same name of all objects. And then we have here, you see the type description, and you can set up a lot of layers below where we can actually have a one-on-one relationship between the layer and the geometry. Okay, now we're covering special components. So this is about a joint component where, for example, in this case, two beams collide somewhere. So, for example, instance 203 with instance 105 collide and create a joint component instance that follows a specific naming scheme, which is in that case 105x203, and the same here. So this is the setup. I think you got the idea here. Yeah, last one before we jump into the showcase is about parent-child relationship. So let's say you created in a reference model stage, in a coordination stage, whatever, a beam which is continuous over the whole surface, which is following a reference axis, and now you want to do segments out of it. Then we can say, okay, this is a parent. We want to keep it. We want to keep it. We don't want to get rid of the information we already created. We want to put new information on top of it. In order to do that, we could now kind of create new components. In that case, they are segments, and define a specific naming scheme in order to define them as a child of that parent. Yeah? So in that case, we have a type ID with a type delimiter. It's almost always the same for a component in general. And then, like a joint, we have, in that case, the parent with a dot, and then the instance name of the child, which is 01, 02, 03, whatever. Okay, that's already it here. I'm going to switch to the showcase project and hope I was not confusing you too much with all the theory behind. We will see in the Q&A later on. So let's start with the project. So what we are going to do is we are going to quickly rebuild this beam project. We have just like what you already seen. We have two different types of beams in two directions, and we have some joints. Before we actually start creating the stuff, I want to show you what we can do with the plugin. So this is the plugin. We have in total 5 different topics or categories. We have stream, create, retrieve, I think that's modify, and utility. And streaming means basically that we receive the information from here. So let's just do that. I'm going to stream some components. They need IDs. We can just grab some and set the GUIDs and see what's the outcome. So yeah, we are streaming now these packages, these components. Come on. And if we deconstruct them or like look into what's there, you see, okay, the names we talked through and also the geometries attached to it. So it's not just streaming the geometry, it's streaming the whole component as a data source, as a class, actually. yeah, what's maybe more interesting also is to stream them by type. So for example, if you want to retrieve the longitudinal beams, you can just create a text lab, say I want to create the L beams, which is the type ID, put it in here. And then you get all the L beams, all the instances defined here in the type. We have also the possibility to apply some regex patterns in case you want to filter for something. Yeah, you can get this one, whatever. Okay, now the joins become interesting because, like, let's say we define some joins here, and you want to get all the joins that are attached to this beam that have a certain relation. Yeah, and you can use that one and retrieve joins thingy, and you get all the information here. All right. Happy to receive questions regarding this later on. I think for now, that's fine. Maybe another thing, maybe we could also retrieve some geometry. It's also important. Yeah, so we put in the L beam and what's in here. For example, the detailed volume. Just write down detailed volume as a layer information. And you get the detailed volume. Yeah, or if we get rid here of the pattern, we should get them for the whole type. We change it to, for example, reference axis. We get all reference axes. So this is the way we can use Rhino as a database. Yeah, that's the whole reason why we do, or one of the reasons why we do components, because we want to modify stuff in a controlled way. All right. So I would say we get started now. I completely get rid of all of this and of this as well. And quickly purging. Right. So, well, yeah, that's the entry point for our planning here. So, okay, I'm not sure what you got last, but this is what we just created. So we created the first component, which is of type grid. And now we want to populate it. So this data container needs to be filled with information. And this grid, which is set up, you can do this however you want to. And then we do the following stuff. We, yeah, in the end, create component members. So we have 8 layers, for example, the axis in X direction, and attach geometry to them. But just let's do that. So I just attach it here and bake it, and you see it's now populating the axis in X and Y direction. So that's a nice thing to do here. I will not go into too much detail here in this showcase. I recently recorded a YouTube series for that, which will be online available next week. So if you're interested in how that works in depth, you can check that out next week. Yeah, but that's the first component we just created here. And now we want to build on top of that. So in order to do that, we go from the context model. Maybe in the meanwhile, we already agreed with the architects that this is the building grid, which will never change, hopefully again, because otherwise we will maybe have to adapt the logic that is built on top of it. All right, so let's go to the next stage, the reference model. And first thing we want to do here is we want to make use of our building grid. Just let me know. Okay, I hide the input for now. We just have now this component in the model, and we want to retrieve the information we just created. So that component is streaming what's already in the model. Yeah, stream by type. We define the type grid, which is here. Stream it, get the information, and then retrieve the geometry. So in that case, we define axis in X, this layer, and get it. And this is axis in Y. So yeah, this is the way how you can retrieve geometry with components. Yeah, and then we do some computation here and compute actually the axis for the beams. Somewhere here, I think. Okay. This is just an intersection between the reference surface and the planes. And then, yeah, we define this type, which is L beam, longitudinal beam, we already saw in the presentation. And we have the components here. You see they are just like, as always, we register component members, and the component members in that case are the reference axis. Yeah. So in the end, before we bake it, it looks like this. So the components consist out of the curves here. And if we switch on the model, you see, okay, they are baked like this. All right. Next step is to create beam volumes. So we recompute and yeah. Now we stream again by types. So we get the grid, we get all the L beams and the transversal beams. And we do some processing on them, compute the raw volumes, and get in the end, yeah, beams with basic volumes. Bake them, and you see now the layer volume and raw volume has been populated here. So the component grows. Yeah? We always refer to the same instance, to a data container, and we fill it. That's basically the principle here. All right, references, and the last step now is already to create the joints. So we have the information we need to define intersections between the beams. And first thing we do here is, again, we stream our stuff and define joints, joint types. And the joint types in that case, yeah, come with a specific name. So like one beam collides with another, and as already said in the presentation, that composes the name of the beam, of the joint, I'm sorry. And to be able to see them better, we just placed in this placeholder. So let's just bake them. And yeah, okay. I think that was, there's still a bug actually, where we need to recompute sometimes in order to create a proper layer tree. Sometimes it's a bit messed up, but usually with a recompute, it's solved. All right. Now that we have these joints, we want to fill them with information, because what we ultimately want to do is to create detailed volumes. And the principle we are doing here, or applying here, is we use the beams in that case, and then we receive for each beam the joint and create like the cutout here. So, and therefore we need to create cutter geometry first. Yeah, so now we have an upper and a lower cutter. The upper cutter will cut this beam, and the lower cutter will cut this beam. And that's the last step we're doing here. So attach it here. Bake it. Yeah, and now the model is already, okay. Sorry for that. Just want to maximize the viewport. All right, so that's the result actually. So we have detailed volumes here. Yeah, all the beams. All right, I think we still have 10 minutes remaining. I was a bit too fast actually. Maybe then we can jump here and have 5 minutes longer Q&A. So you can download the project and the plugin here on Food for Rhino. And there are some basic example files and also explanation tutorials involved. And next week, as already said, we are going to publish the YouTube videos where there is a more hands-on approach on how you can actually do this, how you define component types and component instances. And yeah, the files we just checked through will be attached as well to this project. And yeah, in case you want to get involved a bit more, so as a developer, you can also go on GitHub and just it's an open source project. You can contribute if you want to check it out. Or if you have any issues, then start an issue here, make a bug report or feature request. And in case you want to ask something, you could write us an email or you just go here and start a new discussion. Yeah. So that's it. Thank you for participating. I hope there are some questions we can discuss.
Yeah,
We still have
thank you so
25
much.
minutes.
Yeah, no problem. There are a few questions. Thank you so much for the presentation. It has been really interesting. In the previous webinar, we were also discussing about having the importance of having the file very organized. It was more related to Rhino, and it's also really important to see why it's important to keep all this organization, all these namings very well organized to improve the performance in your workflow, in the way you are able to change things and keep everything correctly. And also when you are working on a team, it's more important. And some of the questions are also about that. The first one was from Victor Crespo, and he asks if there are any standards or reference about the nomenclature, or if it's your own nomenclature.
Sorry, the last one, standard about what?
If there are standards for the nomenclature, for the naming that you apply, or it depends on the project or on your company, or
what we usually do is we just have a 4-character type ID. So we have a railing beam, that can be whatever. And here that stands for kind of BM, beam, RL, railing. It's just like you can do whatever you want to, but usually we do it capitalized, and it's about readability. You don't want to maybe introduce special characters though. So dollar signs or something like that could be messed up actually with regex. Besides that, there are no conventions, no.
Yeah, I'm not sure if it was about the slide exactly, but yeah, this is really interesting. There was another one, I think, that you have more layers, but yeah, probably one of those. Yeah, I think it's quite clear and very well organized and really easy to read it. Yeah, exactly. The next question is from Gu Nguyen, and he asks if do you use write read Excel file for this kind of big data? I'm not sure the data exactly, but if you're using Excel with Grasshopper.
Excel with Grasshopper. So actually we are using, we're actually having a Python library, a quite extended one for doing this kind of projects. This is like, what we do. We define Python classes, but they are working similar to the way the Grasshopper components work. So this is more for us to be able to communicate with clients, so with our models, so that they are actually able to stream information. We are using the Grasshopper plugin itself more for maybe early design stages. And when you want to do something quickly, when you want to set up a structure like that quickly, but if you want to do heavy lifting and computation, we switch to coding actually in the end.
Yeah, exactly. And I think I missed some. I will check them later. But now Jeff is asking if the plugin is similar to what Elephant can do. I know it could be similar, but it also has a lot of differences.
Actually, I can't tell you because I'm not familiar with Elephant, but I will check out.
Yeah, Elephant is more probably for creating layers, blocks, etc. That is also now that Rhino 8 has included in Grasshopper directly. So I think it's different how you create the components.
Yeah, I think so too. I mean, if we look at just a single joint, for example, you see this is like, I go to the properties, and yeah, if we check this component, you see all of the objects inside have the same name, and we discussed the schema, and all of the objects inside are on a different layer. So this one is on the top layer, on the type layer. This one is on the placeholder layer below, and they are assigned one-on-one. There's one-on-one relationship between objects and layers. Yeah.
You are not only creating the layers, but also creating this component with all the different objects assigned to the layer and with the naming and etc.
Yeah.
So yeah, I think that's the main difference. Yeah. What Elephant has is what Rhino 8 has now. That is for creating layers by itself, but yeah, not creating this kind of component. And Carrie James says, can you describe the linkages between the models a little more? Are you linking Grasshopper model, or is Rhino your intermediary?
The streaming part.
I'm not sure what he means exactly. If Carrie, if you can explain a bit more, we can check it. Yeah, because I think it was at the end. I think it's if the geometry you are creating it in Rhino directly, and you import it in Grasshopper, or if it's different Grasshopper files that are creating the different geometries.
You can create the geometry wherever you want to. It's just important that they follow the schema. So what we could do actually, so let's just stream that component. Well, you could actually just create whatever, make a box. Yeah. And then we need to do some things. If we create this box in Rhino and want to make it part of the component, we first need to add it to the group. So now it's part of the component group. That's not enough. So we now also need to like copy the name, because this one doesn't have a name yet and needs to have the same name here. And it needs to be on a specific layer. So what is it? A joint. We can now go below and say, okay, and this one should follow the same schema. Let's say it's a test. That's the layer. And then we just put this extrusion. Oh, we can do this like that. Object layer like this. Okay. Hide it, and you see it's already part of the component. And if we now retrieve geometry from that component with the specific layer information, which is in that case test, yeah, you see we receive the information where we expect it to be on the test layer inside of that type here. Was it clear?
Yeah, I think so. I was reading the next questions because they are quite long and complex. Okay. I'm not sure if you can check the chat to read them because it could be easier. But for example, Hussein is asking if once you have the process complete and if you want to change a specific part, can you change only that part of the revision, or do you need to run it everything again completely?
You can only, you can change it. That's actually the nice thing, which was, let me refer first to the Zen of Python. Special cases aren't special enough to break the rules, although practicality beats purity. And practicality in that case is given. So You mean, if I got it right, it's about now we have a specific situation here, and the cutout needs to be, I don't know, bigger or whatever, but only for this specific instance. Yeah, then you just do that. And you just modify the geometry and you use it. And here, like, yeah, you receive it again. Yeah, it's really, you can really imagine Rhino being just a database. And it doesn't matter how you apply the transformation of geometry, if it's computed or not. You can just fetch it later on and work with that.
Okay, it's a bit complex. So Lish is asking, when regarding Rhino as a database, are you referring component instances strictly to geometries, or do you also see the chance to extend components with additional metadata that could be stored, for example, in the user attributes or elsewhere?
I think we currently have a feature request for that, and it's partially at least implemented already. And this is kind of messed up here with the screen. Sorry for that. Hey, come on. Create object attributes. I think it is like, yeah. Object attributes. And somewhere you can assign it. Yeah, okay. It is in the component member. In a component member, you can actually attach object attributes, and they are, you can also just create with Python Rhino object attributes and attach them here to a component member. And when you bake it in the end, I think it will then also create object attributes. Where are they?
Yeah, I think they can be in the properties, or if it's a block, then you can have the block attributes.
True here. Yeah. I think that's already working, that you set them up, but it's a bit hacky right now. In the future, we might want to have a short video to explain how you can do that there.
Okay. Yeah, and the next one is from Rob Geyer. Are you using your Grasshopper model to simulate loads and stresses within the Rhino Grasshopper environment, or transferring data to another software? Or it's something that you don't do in your company?
Well, yeah, what we usually do is to kind of transform the Rhino models into CATwork models in the end, or prepare the Rhino models in a way that CATwork can properly read them. And depending on the necessity, we might also export some structural models for engineers. And basically whatever you want to define as an interface, we can serve. Yeah. The standard way is we define geometry and attributes in Rhino, and from here we can talk.
The next question is, have you tried this approach in residential high rises for reinforced concrete, or managing reinforcement, MIP, etc.?
No, not that I know.
Okay, yeah, in the questions he explained that he understands that it's more Revit or Beam thinking, but yeah.
Yeah, I mean, in general, there's a ring belling. There's also danger ring belling. So when we are not in parametric or freeform planning projects anymore and are talking about more classical projects like classical building, then we might overflow the complexity, because you can imagine if we are talking always about different types and subtypes and we need to handle them parametrically, that might help for a project like this where we have like 5 or 6 different pieces. But in classical planning projects, we don't want to start with parametrics, because we might have 50 different types or subtypes, and then the complexity just explodes. Then it might be more beneficial to do some classic planning approaches there. Yeah.
Yes. Let me check if I miss any questions. Simon is asking, do you have any tips to optimize computing time in very big projects?
One thing that could help is like just go with this approach. So it's basically about chunking here, right?
Mm-hmm.
You have the context model, you compute it here once, and you bake it, and then it's in the model. Then it's here, and you don't need to compute it anymore at all, except something changes. Then, of course, you need to recompute everything. That's dependent on that. Well, that's the thing. So we compute it, and now we move on. That's the reason why we have different files here and different stages. And same here. So we now when something changes, even if we get rid of the beams of the joints, for example, doesn't matter. Yeah, if something changed in the logic, we still have the beams below, which we need to define position of the joints. They are still in the model and they didn't change. And we don't need to recompute them. We just need to recompute now our joints.
Yeah, yes. And they are just connected by the name, the nomenclature of the objects. So it's baking, and then the next Grasshopper definition is reading from Rhino itself.
Mm-hmm. Yeah.
Yeah, because you are not using hops for connecting the different Grasshopper files, for example.
No, we don't.
Yeah.
And usually it's also a bit slower. It's not like you
Yeah.
start in the morning with the context model
Mm-hmm.
and end with a detail model. It's about, probably a process over weeks and months
Mm-hmm.
where you work in one file and then someday you say, okay, this is now, because you can consider this to be a valid model now with that state, and you can reconstruct it always from here.
Yeah, that's very interesting. Instead of continuing the same definition, just keep it clean and save it and create the next part on a different definition. But yeah, I think that's all of the questions. I'm not sure if you need to add anything else.
I just maybe want to thank you, my colleagues, and especially Fabian and Hanno for coming up with this idea in general. I mean, they set up this approach 15 years ago and did all the projects, the big projects with them. Yeah.
Thank you so much. I think it has been very interesting. I'm not sure what happened in the middle of the presentation with the connection, but I think it shouldn't be a problem. I will try to keep it clean in the recording for YouTube. So I think it could be quite easy to understand the part that was missing there. But it was like 30 seconds, no problem. Thank you so much
right.
to Bastian, to Fabian, to everyone in the team. Have a nice afternoon or nice evening, because I see there are people from everywhere in the world, same from Vietnam, from South Africa, from Philadelphia. So many people from everywhere. Thank you so much. Bye bye.
Thanks a lot. Have a nice one. Ciao, guys.
Bye.